Hey everybody, welcome to today's update on Daily IoT. On today's update, I want to talk about sort of the struggles of going through and choosing components for our hardware product. And so I've been going through, I'm still looking to have another company finish off the design. I've gotten it, I'm going to say 90-95% there hardware-wise as far as the schematic. But one of the things that I was trying to do and was going to, at an earlier point, try to get all the way through was the power block design. And so this concept of taking voltage from the battery and turning it into the voltage that I will need to run the puck, specifically the P1 and the screen and things like that. And so I was going through and looking. John at Predictable Designs had sent me a couple of voltage regulator suggestions, and I had reached out and said, I'm looking for something that has real low quiescent current. I talked about this in a previous episode. And so he sent me another recommendation. I was reading through that data sheet. I was trying to get, like I said, the schematic all finished up, and I realized that the data sheet had something that was a little bit confusing. Some of the voltage regulators that I've looked at in the data sheet, there is a quiescent current curve. And so based on the output current that the regulator is driving, the quiescent current will change. And so this particular one, it is the LD39100 LDO from ST, I believe. ST. Has a listed 20 microamp quiescent current. And I thought, oh, that's perfect. That's just what I need. That's lower actually than what I was looking for. I was looking for a target around 50. And so, but as I looked in the data sheet, it said that the no load quiescent current is 20 microamps. The quiescent current from 0 to 1 amp, which is the entire output range of this particular voltage regulator, is 200 microamps. And so when you read that, 0 to 1 amp, that says that in the datasheet it says the no load, which I would say 0 current, quiescent current is 20 microamps, but also 200 microamps. And so I had this question of which one is it? Because the datasheet was not very clear. And so I sent a request out to ST to say, hey, do you have a curve for this, or is it 20? Is it 200? Like, can you help me out here? And I got this back. This was let's see, how long did it take? It took them about 2 weeks to get back to me, which is fine. I just submitted this on their online forum. And basically they said, I don't know, try it, which I was a little disappointed in. They explained to me like, oh, this is typical current. They explained a bunch of things that I already understood the meaning of when they say typical current and things like that. But they said, let me quote it here. The typical quiescent current would be 200 microamp with a 100 microamp load. So as part of my question, the sleep current of the P1 and everything should be somewhere around 100 microamp. And so in that 0 to 1 amp range, I was saying at 100 microamp output, what's the quiescent current? Like how much current is the regulator itself going to be consuming to give me that 100 microamps? And so they had said with 100 microamp output current, the typical quiescent current would be 200 microamps, but with such low sleep current, you could possibly be closer to 20 microamps than 200 microamp. But the best way to find out would be to set up the circuit and measure it, which is totally fair. I get it. But I was hoping that as the manufacturer of the part, they would have some better, like I said, some graph that maybe they didn't publish in the data sheet that shows the quiescent current. Because what that means to me is with no load, it is 20 microamp. That's the listed in the data sheet. But anything, even microamps of current, if you're pulling out of the voltage regulator, now that thing is going to start drawing up to 200 microamps. Now that's an order of magnitude, right? 20 to 200. And so that's huge to me. If I'm pulling 200 from the LDO, while I'm in sleep, then I'm losing unacceptable amounts of battery life. And so I'm going to need to consider a different voltage regulator and maybe even go back to considering using a switching regulator instead of a linear regulator. And so why does this matter? Set it up and measure it. So I could do that. I mean, I can't right now because I don't have the rest of the circuitry, right? I don't have the P1 and the e-paper display hooked up in the configuration that it will be in the puck. And so, but all these things cost money, right? I'm bootstrapping and paying for all of this. And so the reason I'm trying to be so diligent in researching these things is because let's say I pick this one, 20 microamp quiescent current. That's perfect. That's below my spec. Go ahead and put that in the design. I get it all done. PCB is designed around that, copper fills and vias and things are created. It's printed out. I do a run of boards. I get it. And then now I have it and I'm measuring it and I realize, oh crap, even in sleep mode, I'm pulling 200 microamps. That's not even going to be close to the battery life I hope to get out of this thing. So now what do I have to do? I have to pick a new voltage regulator. I have to redesign, redo the schematic, which shouldn't be a huge deal. But then the big deal is I got to have that portion, at least, of the printed circuit board redesigned. All this costs money. Then I got to have another batch of those fabbed. And so just little things like that, one component, and then you get it and you figure out that it's not what you want. Now I got to spend a lot of money to do another iteration. And so I'm trying to minimize the number of iterations I go through here so that I don't spend as much of my own money. Now, if I got some VC guy writing me checks, it's like, I don't care. Try with that one, try with 4 other regulators and have boards designed for all of them. Whereas I'm spending my own money, I'm trying to be more thoughtful and do the research up front so that I can choose the parts. I'm not naive to the fact that I'm probably going to get something wrong and we're going to have to do a revision, but I want to minimize those number of revisions as best I can by spending in a little bit of time up front. Measure twice, cut once, that idea. And so that's the update. We're still looking. It looks like this voltage regulator is not going to work out. The second part of this is I don't have a way to measure microamp level currents. These meters I've got, they're not going to reliably measure down in that range. And so I don't have the equipment to measure the current usage of that particular voltage regulator, even if I had a test circuit set up. And so that's another thing that I need to figure out with whoever I'm going to be working with, figuring out the cost of that. Can they do that for me, how much that's going to cost and things like that? Do I need to just buy myself something like a microamp or microcurrent, I think it's called? Dave Jones in Australia sells those to be able to set up a test circuit here and test the current draw to help me choose components before we get into PCB layout and fab and things like that. And so that's it. That's the update on today's episode of Daily IoT. Question of the day: do you have a favorite voltage regulator? This has got to be the lamest question of the day. I can't think of anything else, but do you have a go-to voltage regulator that you like to use? Stick it in the comments below. Would love to hear from you. Also, if you do hit that subscribe button, please remember to send me an email, kevin@sidwar.com. I love to hear from the people that are on the other end of clicking that button. Thanks so much again for watching Daily IoT, the show where together we're learning how to make the Internet of Things one day at a time.